Day 7, nonlinearities. Okay, so we're going to go through sound waves. Now I'm going to stop horsing around with this thing. So we'll go through sound waves because I want you to do it on the homework to derive the sound wave dispersion relation. So I'm going to go through it kind of quick because it's kind of complicated and there's a couple of steps to go through. But there's some important steps that we do that make sound waves work, that make other things not work. So we'll talk about sound waves and I'll highlight some of those important bits. And then we're going to talk about method of characteristics, which is the thing that I started on Thursday and kind of went kind of fast through, and I think it was, we're just going to do that again so that I can highlight a couple of things. 3, then we'll get into shocks, and we'll derive the Rankine-Hugoniot relations. And then we'll talk about explosions and how the New York Times published highly classified information in the yield of the first nuclear weapon. They published it unknowingly on the front page of the New York Times, but only if you actually knew what you were doing could you back out what the energy is. But I'll show you how they inadvertently did that. And then I'll show you how to make a supersonic ping pong ball launcher. I'm not actually going to show you how to do it. I'm going to show you the math, and then you have to figure out how to get PVC to do what you want. But so we'll talk about how to make things go supersonically. So, okay, sound waves. I don't need that. I have all the things I need over there. So please stop me if any of this is unclear or confusing, or my notation sucks, because it does that. Let's use green. This should show us pretty good. Okay, so how do you derive sound waves? So you start with continuity in Euler. And then we have a background you have a uniform background solution, and we know that this state solves the equations. So I have some solution that is a solution to these. We then linearize around. Let's call this uniform solution, we're going to call it Q naught. And Q naught, this is shorthand for rho naught, P naught, and V naught. Okay, this is just a bucket of stuff. This is just, I'm shorthanding this. Q is everything. That's my whole state vector. So we linearize around Q naught by plugging in Q naught plus delta Q, where this is tiny little bits in this. I used Q1 the other time. I'm going to use delta Q now just to change up the notation, because you're going to see it all kinds of different ways. So I want you thinking about what the quantity is and not how I call it, because people will do this with Q naught, they'll do it with Q1, they'll do it with epsilon Q, so they'll do this in a bunch of different ways. So we linearize around Q naught. So Q naught is our background solution, and delta Q is little. This is a small perturbation. This is perturbative. How do you spell perturb? Then we do a little bit of algebra to make one equation, because this gives us two equations. So we do a little bit of algebra to get one equation, one linear equation. This linear bit is important because the linear bit is why the next part works. So then the last thing you do a little bit of algebra to make it's linear up here. let me emphasize one linear equation. It already got linear earlier. Then, this part isn't super interesting, but the next part is Fourier analysis. And so with the Fourier analysis, rho of x and t becomes rho naught e to the I kx minus omega t. You could call this plus omega t, but then it doesn't make as much sense. The minus is a useful convention. So you plug this in, and one of the upshots of Fourier analysis is time derivatives goes to I omega, and space derivatives goes to I k. And this is actually minus I omega because of the minus. And then you're left with the dispersion relation. Omega versus k. And from that, you can find group and phase speeds. Is that everything? Yeah. So when we did sound waves, we did a bunch of things. And it's really, I'm going to take my, it's not a ton of things, but it's a lot of different steps when you spell it all out. So I linearize, means get rid of all of the nonlinear terms, all of the higher order terms, which puts constraints on my solution. That means my delta can't be very big. And then I do Fourier analysis. That's really the important bit. The important steps are linearization and Fourier analysis. The only reason that Fourier analysis works is because we linearized. If you try to do Fourier analysis without throwing out the nonlinear terms, it goes south. Let's see. Do you guys want me to go through this derivation with the details right now? Or would you rather have a stab at it for homework and see how you do?
I'd rather you go through.
You want to see it now? All right, okay, let's do that. So we're going to leave this up here. So this is our form. The reason that I'm going through this, like part of the reason that I'm going to go now spend another whole day on the same material, like I'm going to just give you the same lecture that I gave you a couple days ago. I'm going to do it a little bit more smoothly, and you have seen it already, so it's more familiar. But more importantly, this is a machine. This is a machine that you turn the crank on, and you can put other equations into here and get other results out. So this is a set of processes that people use all the time to do everything, to do a lot of things in physics. So the general things are you start with the solution that you know. Maybe it's uniform. Let's put this in parentheses. It's uniform today, but sometimes it's not. Sometimes it's something interesting. The linearization is important. That's the generalizable process. The Fourier analysis is the generalizable process. So that's the process that you'll use a bunch of times in a bunch of different places. And we'll use a bunch of times. So we're going to get to chapter 7, and all of this will just be a line. Here's my equation. I make this assumption, linearize in Fourier, dispersion, stability. So that we'll get more out of this. So we're going to do this a whole bunch. Oh man, somebody very nicely wrote the equations that I need right here on this board. It's nice being the only one here. So I only need these first two. Let's start. Okay, so continuity, d rho dt plus div rho v is 0. So this has the form of a conservation law. So this is the partial rate of change of something plus the divergence of its flux. So this is the stuff coming out the surface. And then think about volume integrals. This divergence, you integrate, turns into a surface. So this is really the surface integral. dv dt, this is chain ruling out the full time derivative of the velocity, and here is my force. Now for Navier-Stokes, we would have plus nu del squared v, but we'll ignore that for now. How do we know we get to ignore that term? What is the one term, or what's the one quantity that determines how important that term is relative to this term? the viscosity, but there's another number that links both the terms, and that's the Reynolds number. So the Reynolds number, remember, is LV over nu. And you're right, it's the size of the viscosity, but it's the size of the viscosity relative to the other size scales in the process. So if this is a very large number, then nu is clearly small. Now, small versus get to throw it out is different. But we're just going to throw it out right now. Okay, so here's my equation.
I have a question.
Yeah.
How large does the Reynolds number have to be before you determine whether you throw up that last time?
Well, formally infinite. So if it's like 1,000, you can probably throw it away because this term isn't going to dominate. Unless you need to be really careful, in which case you may still need to keep it. So I typically simulate things that have Reynolds numbers on the order of 1,000, and I throw this term out. And there's reasons for me throwing this term out that has to do with the turbulence, but around 1,000 is a good ballpark. Much, much larger than that, you're probably okay to throw it out. Much, much smaller than that, you cannot. Around 1,000, it's kind of dubious. Okay, so the first thing we do, we know that d by dt of rho naught plus div rho naught v naught equals 0. And okay, b is a vector and naught is a vector. So this is my background solution. And also I have d by dt of v naught plus v naught dot grad v naught equals minus 1 over rho grad p naught. Now, this equation is kind of dumb because this is the gradient of a constant, and so it's 0, and v naught is 0, so the left hand is 0 because it's 0 equals 0. So, but that's okay, but this is our background solution. It doesn't have to be trivial. So this is a background solution. So the next thing we're going to do is we're going to send rho goes to rho naught plus delta rho. I'm going to use delta rho this time, which is a super common notation. Delta just means little, and so if you get 2 deltas, that means really little, and you can throw it out. V naught, or V goes to, let's call it delta V, and P, well, we'll deal with P in a second, but we'll say that P goes to P naught plus delta P. So the first thing that we'll do, so the first thing we'll do is just plug all of these into my constituent equations. Yeah.
Why doesn't V go to V naught delta V?
Well, V naught 0. It does. Good question. So I could put this as V naught plus delta V if V naught was interesting and not 0, but I'm just going to call it 0 here because it's easier. So if you want to generalize it a little bit, you can leave that there. So we drop into here, and we're left with d by dt of rho naught plus delta rho plus this term, div rho naught plus delta rho times, well, v naught, we're just left with delta v equals 0. And then the other one, Euler's equation, delta v plus delta v dot grad delta v equals minus 1 over rho naught plus delta rho grad p naught plus delta p. Okay, I didn't think about anything that I just wrote down. I just took the equation that I know and I plugged in these things. So this is just turn the crank on the machine. Then we got to think a little bit. So here we plugged in. Now we need to linearize and get rid of the background solution. So let's talk about this first equation here. So the first term, d by dt of rho naught, several ways to think about this. This is my background solution. So it's going to cancel out with something over here because of this. Or I can just say it's 0 because it's constant. Both are fine answers. Both are legitimate answers. And then with this term, this expands to rho naught delta v plus delta rho delta v. So which one of these two am I going to throw out?
The delta P.
The second. The delta rho, delta V. So this one gets thrown out. Why? Because it's small. And here is some magic. Like there is some magic here when throwing things out. Because sometimes you throw things out and you shouldn't. Sometimes it's not always easy to tell if it's small enough. But it's a lot of the time as a physicist, you can just do it and pay the cost when you screw it up. So we're just going to throw these out. Since it's a sound wave, the density isn't changing very much from the sound of my voice, right? You're not feeling that on your ears. So it's a pretty good assumption that it's small. Okay, so now this equation, let's rewrite it, becomes d by dt of delta rho plus div, the only thing that's left is rho naught delta v equals 0. And then this next term, d delta v by dt, that's what I want. Delta v dot grad delta v. So this term is a problem child. It causes problems. I'll show you. Yeah, we'll talk a lot at length about why this term is a problem. But what can I say about it right now?
Small.
It's small. I got 2 deltas. So it goes away. Yay. Okay, now this last term, you got to do a little bit of work because you got to expand this 1 over rho naught. So you got to expand this. Let's play a little mini game on the side. 1 over rho naught plus delta rho. We have to do a Taylor series on this. I only remember a couple of Taylor series. I remember sine and cosine and 1 over 1 plus x powers and stuff. So I don't remember a ton of Taylor series. But this one I remember because I use it all the time. 1 over rho naught plus 1 over 1 plus rho delta rho over rho naught. Okay, so I know 1 over 1 plus x is 1 minus x. That's a Taylor series, and I can prove that if you want. But actually, if you want me to prove this, then I'm going to make it a homework problem. Because this is one of those things that you should probably just like ingrain in your head, just like grind it into your carpet, that this Taylor series. So then this becomes 1 over rho naught minus delta rho over rho naught squared. Does everybody see that? Then, okay, let's check about this term. So I've got a bunch of things in this term. So this is 1 over rho grad p. So grad p0 is going to go away. And you can think about that as I'm going to use it to cancel out my background solution, or it's constant, so the gradient is 0. So I'm just left with the grad delta p here. So I'm going to multiply this term times grad delta p, which means this second term goes away. Because this is a delta rho, and I'm going to multiply it by a delta p. So when I Taylor series the right-hand side here, this turns into just 1 over rho naught grad delta p. Does everybody follow that? Yeah.
So why doesn't the delta p go away as well?
The delta p? That's what I hang on to. That isn't, it's not uniform, so its gradient is non-trivial. And I got a delta p times a rho naught thing. So let me expand this out a little further. Do I have another board back here? No, they'd be sad if I wrote there. So this term here is 1 over rho naught plus delta rho grad p naught plus delta p. If I plug in the Taylor series here, then I'm left with 1 over rho naught minus delta rho over rho naught squared. This is from the Taylor series of this one. Grad p naught plus delta p. And again, super important to separate your p's and your rho's. So we expand this out, we get 1 over rho naught grad p naught, which that's part of the background solution. So I'm going to use it with the other parts of the background solution. Or it goes away because its gradient's 0. So that's the first term. Minus delta rho over grad p naught, delta rho over rho naught squared grad p naught. That one goes away because this is 0. If you have a non-trivial solution, then this term will give you some headache, but not a lot of headache because it's linear. But this one goes away because p naught is 0. And then, so that's the first guys. And then the second guys are 1 over rho naught grad delta p minus delta p over rho naught squared grad delta p. And so this term goes away because it's got 2 deltas. And this is the only term that survives. 1 over rho naught grad delta p. Does everybody get there? So holler if you want me to do any of that slower. I'm going to clean this up just for clarity. Okay. So here's our first linearized equation, and then linearizing this equation, we're left with partial t of delta v equals, this term's gone, minus 1 over rho naught grad delta p. Okay, so these equations look pretty similar to the beginning ones, but we don't have anything where I've got an interesting variable times an interesting variable. This is all interesting variable by itself, interesting variable by itself. Rho naught is not an interesting variable. It's a constant. Yeah.
I have a question.
Yeah.
So 3 lines up from the last line. No, 1 line up from that. Sorry. So you said that first rho naught, you let it go to 0, but then the next one we kept it.
Yeah.
How come we could do that?
Well, this one is 0. This one goes away because it's all by itself. So the time so it's constant. So it goes away.
Oh, okay.
But this one over here gets multiplied by a delta v, and the delta v means that it's not part of the background solution anymore, or it's not constant anymore. So it's hanging around multiplying by a delta v.
Okay.
Yeah.
So that's delta d, or partial t delta p, right? Above the v. Yeah. Right.
This is rho.
Next to it, is that to the left of it? Is that a delta?
This
Yes.
is a delta, yes.
Okay.
This is d by dt of delta rho. So the little quantity in rho. Okay, so that's step 1, linearize. And this is the bit where in textbooks, they always sweep this, they never spell this out. If you're reading a paper or a book or something, they always just say, we linearize, and we're left with some of this. The reason books will do that is because this is a process that you always go through and you always do the same thing. And once you've done it a couple of times, you can kind of do it in your head just by looking at the equations. Because everywhere I see, like here, I know I'm going to throw some stuff out. Here, I'm going to know I'm going to throw some stuff out because I've got 2 things. Okay, so we'll leave those guys up here. I'm going to erase here and start again. Let's recopy our linearized equations. So our linearized equations is d by dt of delta rho plus div rho naught delta v equals 0. Formally, these are vectors, but I'm going to move to 1 dimension in like 4 seconds. And then dt of delta v equals minus 1 over rho naught grad delta p. And then, now we got to do a little bit of algebra. So I got too many variables. Let's get rid of p. How do I get rid of p? Does anybody remember what I did? I used chain rule to turn this p into a row. Now this is important that you're careful about this. This isn't something that you always get to do. It's only something that you get to do because we decided that our perturbations are adiabatic. And being adiabatic means that p equals rho to the minus gamma. So pressure is only a function of density and not of temperature as well. Then I can say grad p equals partial p partial rho grad rho. So in this algebra section, Grad p goes to c squared grad rho. So we're going to call this a number. Let's call it c squared for now, and then we'll see why I get to call it something squared in a minute. Then the second thing in this algebra is cross-differentiate and subtract. A little bit of algebra there. So we'll get rid of that, okay? So I'm just going to doctor this guy here. C squared delta rho. There might have been a delta missing from what I was saying there, but it doesn't matter. Okay, everybody good with these two equations? Now I've got two equations and two unknowns. So we'll get rid of one of the equations. So I've got time on density, space on density and velocity, time on velocity, space on density. Let's get rid of velocity. So it's a grad here and a time here, so I need to do a d by dt of this one and a grad of this one. And then I'm left with dt rho squared, so now I've got two time derivatives, plus dt grad rho naught delta v equals 0. And then this other equation becomes dt grad delta v, let's put this on the other side, plus c squared over rho naught grad delta rho equals 0. Oops, squared, because I took the grad of this one. Okay, I got a rho naught here and a dv. This dv is by itself. Everybody follow that? So I can multiply both sides by rho naught. The right-hand side doesn't do anything. All that amounts to do is moving the rho naught to this term. Rho naught is constant, that's what we said, so it gets to go all the way inside all of these derivatives. Now I have these two terms are the same. And now when I take the difference, they go away, and I'm left with d squared t rho minus c squared grad squared rho, delta rho equals 0. Okay, this is important milestone number 2. Now I have an equation. So I got this equation because I linearized something. So this whole stunt of linearizing things basically turns everything into an oscillator. It makes everything go up and down. It turns everything into sines and cosines. There's several ways to see why it does that. But we can see it here. So everybody comfortable with this algebra step? It's not particularly painful, but there's a couple things that you got to do in the right order to get it to look like this. Now, we have this equation. Let's promote it up here. So I have d squared t rho minus c squared. Let's do work in one dimension now. dx squared rho equals 0. Now, a lot of times you'll see books drop the delta here because I no longer care about the background solution. I no longer care that this is perturbative. This is the thing that I care about. It's delta rho, but a lot of times books will just drop the delta and just start talking about rho because this is the thing that you care about. The fact that it's added to some mean doesn't change the physics. I'm going to keep them. Even though when I'm working, I usually let them fall away at this point. So now what do I do? So I did this kind of slow, but it's a process you'll get fast at. So now the next step is Fourier analysis. So we say that delta rho equals rho naught e to the I k x minus omega t. So this is a thing that I'm allowed to do because the Fourier modes completely described functions. So if you have a function on the real line, it is perfectly described by its Fourier modes. So I can switch delta rho. Delta rho is a function of x and t. This is equal to the integral of, we'll call this rho hat of k, e to the I k x minus omega t, d k d omega. So I have two Fourier transforms, e to the I kx and e to the I omega t. So I've got two Fourier transforms that I'm doing. This is rho hat is a function of k and omega. Now rho hat doesn't really matter for us because we don't have any coupling between the modes. So it'll kind of go away. We'll just say that rho hat is rho naught. That's our mean. We'll just deal with one frequency at a time. We can do this because the equation is nice and linear. So I can deal with only one frequency at a time. So what I really do is I take this, which is actually an integral, and I stick it in both of these places. And then the differential operators act on the exponential, and they bring down an I omega and an I kx. That's what I'm actually doing. But what I'm going to just write down is I'm just going to swap this dt. dt goes to minus I omega, and dx goes to I k. Does everybody follow why I get to do this? If not, I can do it slower. You got a confused look. Do it again, or you good? You good? Okay. I couldn't tell if that was getting through it or you're getting stuck.
Yeah, I was getting through it.
Yeah.
Thank you, though.
No worries. Yeah, and I don't mean to put you on the spot. I just wanted to make sure I didn't start talking if you were still working on the last thing. Because this is kind of magic. It's like, this is where the magic happens.
Is that a full derivative or a partial derivative?
It's a partial derivative. Because the full derivative brings in the other stuff. Now I'm left with, okay, I do it twice, so it's squared. So the minus I squared is just minus 1. So I get a minus omega squared times rho naught e to the I k x minus omega t. And then I get a minus k squared, but I also get a c squared. So I get a k squared c squared rho naught e to the I k x minus omega t equals 0. So all I've done is taken this, stuck it in here, took a bunch of derivatives, and left with this guy again. And then I get to cancel this out because we assume that the density is not 0 anywhere. This is a truth that hydrodynamics hates 0 density. Nature doesn't care. Nature will go to 0 density just fine. Actually, that's a lie. Because when you go to actual 0 density, then you get quantum mechanical fluctuations. So we're left with an equation. This cancels out. It's just omega squared plus k squared c squared equals 0. And this is my dispersion relation. And then the group velocity, the phase velocity is omega divided by k, and the group velocity is d omega dk. They give you the same answer for sound waves. For other kinds of waves, they don't. Okay, then we're done. So this tells us what our phase speed is. So then you can see if I divide omega by k, I'm just left with c. So my phase speed is just c. That's the sound speed. So the speed of this wave is c, which we got a page earlier. C is dp d rho. Turns out that's the speed of sound. If you think about that, dp d rho goes like the speed of sound because that's the pressure force versus the inertia force. Anyway, okay, does anybody have any questions about this board of stuff? Yeah.
Wait, just one really quick question. So the group
Yeah.
velocity is the partial of, what is that? Omega over partial of k. Okay.
They're both omega over k. One is just a derivative, the other one is a derivative and the other is just divide. Yeah.
So what is the difference between root and phase velocity?
This is an excellent question. Oh, I should pull up this. I should turn this thing on. This is a really good graphic on the Wikipedia. Let's see if I can figure this thing out in 5 seconds or less. It always took me a minute beforehand. Let's see. That'll show you this excellent graphic.